Chapter 16 deals with nuclear magnetic resonance, which we call NMR. And this is one of the most powerful forms of spectroscopy and gives a lot of information about compounds. This image is just kind of a Cliff Notes version of NMR and how you can read spectra, and we'll get to what these things mean in a while. Nuclear magnetic resonance, or NMR, also is known as that giant instrument down in the corner of Crawford. So NMR involves interactions between electromagnetic radiation and the nucleus of an atom. And we can use NMR with any nuclei that have an odd number of protons. The most common is proton, or HNMR, and then this is the CNMR. But we can also use it for nitrogen, fluorine, and phosphorus 31 NMR. It's one of the most powerful methods of gaining structural information about organic compounds. So IR gives you information about functional groups. NMR can show you functional groups, plus how all of the carbons and hydrogens are put together. Or if you're looking at different nuclei, you can look at how the nitrogens are fluorines or phosphorus. But for this class, we'll just be doing proton and carbon. Atoms with an odd number of protons or an odd number of neutrons have nuclear spin that can be probed by NMR. So hydrogen has one proton and has a nuclear spin. And the spinning proton is kind of like a rotating sphere of charge, which will create a magnetic moment. So it just keeps spinning, the hydrogen does, because it is odd number of protons, and it creates this magnetic force that you can see developing around here, kind of like a magnet here. So we have this magnet with the north and south poles, and it is generating this force field around it. So when you have a magnetic field that is applied to a nucleus with an odd numbered mass, the spin of the nucleus will align with the field, or it will oppose it. So if you have hydrogens floating around and it's just kind of free for all, everybody swimming in their own direction, doing their own thing, but then you apply a magnet or turn a magnet onto it, and they will either shoot up or they'll shoot down. So you have these that are going in the same direction, and then you have forces that are opposing in the down direction. So the blue arrows represent the magnetic field that is applied here. As the magnet is applied, there's energy that is given off. You have the A and then the B shooting down towards alpha and the beta shooting in opposite directions. And that will give off an amount of energy which can get absorbed and then give off information about the nuclei. So not all nuclei absorb frequency is created equal. So every atom or nuclei will absorb different frequency, which makes it super great for us because then we can use that to differentiate CHs from OHs. So all protons will have this diamagnetism. They'll behave differently when a magnet is applied. A proton is exposed to a strong magnetic external field here. And then there's a weaker induced field that's circulating from the electron density. And then the proton is shielded, or it creates a net magnetic field that's smaller than the external one. So the shielding that happens is what's going to tell us what kind of environment the protons are in. To get a proton spectrum, you have to use a deuterated solvent. And what that means is that instead of using chloroform with the hydrogen here, we're using one with the deuterium. A deuterium is kind of like a hydrogen, except it has an extra neutron. So it's a little bit heavier, and these also will not interfere with our signal. So if you wanted to take an NMR spectra, it won't show up the way a normal hydrogen would. So we tend to use these solvents. The most popular is chloroform D, which we'll use in lab, but you can also use these other ones here. So you're going to add a small amount of sample into a tube, place it into the NMR, which kind of looks like this. The one that we have is also cooled by liquid helium. So that information goes from the instrument into a computer and generates a spectra that looks something like this. And this has a lot of information, and right now it just looks like gobbledygook to you, or maybe a bunch of fingers pointing up and down. But things that you can get from spectral information include number of signals. And the number of signals tells you about the number of different types of protons. So again, the number of signals tells you the number of different types of protons. So if you had 2 different types of protons, you would get 2 signals. This particular spectra looks like there are 3 different types of protons. You get a signal location, or the shift. So the chemical shift here is in parts per million. A proton that shows up in this range is feeling a different environment than something that shows up in this range. Down here, there's not as much electron density around the proton, but up here there is. So that tells us something as well. We also get signal integration, or a signal area. So if I were to look, and the integrations aren't on here, but that tells you how many types of proton are on a particular carbon. And we also get signal shape, or the splitting pattern. And that will give information about the next door neighbors. The protons with different electronic environments will give different signals. So in this structure here, this is a symmetric molecule. These 4 protons are chemically equivalent. Because they are symmetric, they are seeing the exact same things. And this one here is a different environment. These are all HAs. And the hydrogens that are on this carbon would be HB. And the same with this one. So we would only see 2 different signals here. And that's because there's symmetry and those are the same. In this molecule here, this would be HA because it's seeing an oxygen. This one is seeing an oxygen as well, but it's also seeing 2 other carbons, so this would be HB. This is seeing a different environment than any of the other ones. This is HC. We have HD and HE. So this one has 5 different signals. So if you have symmetry, then they'll see similar environments. You might have less signals. So if I look at this compound, I have 3 carbons on either side of the carbonyl. So this has symmetry. So we would have 1, 2, 3 different signals. This is HA, HB, HC, HC, HB, HA. So shielded protons have a smaller magnetic force acting on them. So they have smaller energy gaps and so absorb lower energy radio waves. So these are your lower energy protons down here. This is higher energy. So these are deshielded protons, which pretty much means there's an electron-dense environment. So it could be from oxygens or pi bonds or benzene ring. These are low energy, which has less dense electron environments. So your CH2s, CH3s, those are going to be in the lower regions. So alkane protons generally give shifts around 1 to 2 ppm, and they can be shifted downfield when nearby electronegative atoms cause deshielding. So if I have just methane, that proton will show up at 1.0 ppm. If you add an iodo group, that will increase the electron density, so that increases the ppm. A bromine, which is more electronegative, will bring it to 2.7. This is 3.1 for chlorine, and with fluorine, it's 4.3. And then it's an additive effect also, just like acidity. So you have 1 chlorine, it's 3.1. If you add 2 chlorines, it goes to 5.3. 3 chlorines brings it up to 7.3 ppm. And then with this particular example here, the protons that are closer to the chlorine will have a higher ppm. So these are 3.3. This one right here, which is a little bit further away, is 1.6. So it can still kind of feel the chlorine electron density pulling it, but it's not really felt very far out here. This is 0.9 ppm. Okay, so this is the table that you'll get, and this was on the back of the IR sheet that you got in class. This is not something that you will need to memorize, but you can see all of the protons and where they might show up. So down here are carboxylic acid protons. So if you ever see protons that show up over 10 and into 12 ppms, you should know that those are carboxylic acid protons, because it's not in your usual range, which most of our protons are down in the region over here. Protons around 10 tend to be aldehydes. The benzene protons show up between 6.5 and 8.5. If you have H's on double bonds, those are in this range. Alcohols kind of have a wide spread depending on what they're bonded to. And the other most common ones that you will see are these here. These are CH3CH2, so this is your sp3 carbons. And then you're going to see a lot of these. The Z stands for a C, O, or N. So for example, if you had a hydrogen that was next to a carbonyl. So this here, those ones would generally show up around 2 ppm. So the integration or area under the peak quantifies the relative number of protons that give rise to a signal. So a computer usually calculates the area representing with a step curve. So this curve here tells you the height of the integration. Usually they'll give it to you in a number. It might look like these integration values below here, which seems like a lot of protons on one particular carbon. That's the way the computer calculates it. Usually the computer operator has to set the integral ratio. And the way that you determine how to do that is you kind of look for a common denominator here. So if I divide all of these by the smallest number, which is 27, this would be about 1 proton. This is 1.5, this is 1, and 1.56. So this is telling us there's 1 proton on this particular carbon that's like this. This one has 1.5. This has 1, this is 1.5. But we can't have 1.5 protons. If we multiply all of these times 2, this becomes 2H, this becomes 3H, this becomes 2H, this becomes 3H. That seems more reasonable to have 2 hydrogens on one carbon, 3 hydrogens, 2 hydrogens, 3 hydrogens. So we have 2 CH3s and 2 CH2s is what we're getting from integrations. So the integrations are relative quantities rather than an absolute count of the protons. If we were predicting the H shifts and integrations for this tert methyl ether, these are all HA. Those are the same. This is HB. So I have 2 types of signals. Because all these HAs are attached to that same carbon, they're all feeling the same environment. So for HA, that ppm is probably around 0.9 ppm. And there are 1, 2, 3, 4, 5, 6, 7, 8, 9 of those. So that integrates to 9H. This HB proton is next to a carbon on an oxygen, so it's going to feel some electron density. This one's probably around 4 ppm, and there's only 3 there, so that will be 3H. For this one here, there's symmetry, so I have HA, HB. So there again is 2 signals. For HA, that is next to a carbonyl, so if we look back at our table, hydrogens that are on carbons next to carbonyl are usually around 2.0 ppm. There are 2 of these on this carbon and 2 on this one. So the integration can be 2H or you can call it 4H. And for HB, that is going to be around 0.9 ppm. So if I did 2H, this would be 3H. And then if you were doing the double, then it would be 6H. Multiplicity results from magnetic effects that protons have on each other. So HA can see HB. This one can see the one next door. So that would show up as a doublet. So you have the N plus 1. So if HA sees HB, and you add 1, so this is N, that equals the doublet. This HA sees 2 protons, so N equals 2 plus 1. So we have a triplet here. So that's because HA sees the 2 protons, so we get a triplet. If you have 0 neighbors, that's 0 plus 1 equals 1 peak, 0 plus 1. Those are singlets. This is typically a singlet that you would see on a hydrogen. These ones that are broader, those are OH or NH. So most carbon, hydrogen, and proton peaks are very sharp. So here's 1 plus 1. We get a doublet. 2 neighbors plus 1 is a triplet. 3 plus 1 is a quartet, etc. So we get the sextet. This is 6 peaks. This is 7. So you can count 1, 2. And these ratios of the peak heights are also relevant to that. So if you saw something like this, this is not a quartet. It has to have this specific ratio of things. Okay, so 3 key things that you want to remember. 2 key things. Equivalent protons cannot split each other. So because these are the same, you can think of these as all HAs. This HA does not see a whole bunch of HAs here. It sees nothing. So this would show up as a singlet. And then to split each other, they must be within a 2 to 3 bond distance. So with this HA here, that one can see HB if they're a little bit different environments. This HA can see this HB, but this HA cannot see this HB because it's 1, 2, 3, 4 bonds away, so there's no splitting. This one will have splitting. Sometimes there's recognizable patterns that stand out in a spectrum. So if you have a CH2, CH3, this will show up as 2H quartet. And then you have a 3H triplet. So that is really a good indicator of a CH2, CH3 group. If you have this isopropyl group where it looks like R like this, or this one H, and then you'll see this septet, and then you'll have a 6H doublet. And then we saw this one earlier. This one is the 9H singlet. So if you see these patterns, that's going to give you a good hint about what is in your structure. Some splitting you won't see for protons, especially if they have hydroxyls or a proton that is labile or exchangeable. So that means it can switch out if you have trace amounts of acid. So the broad peaks are due to blurring or deshielding of protons. So if you have an OH, we know that if you add acid to that, that can become O-, and that can get lost. So we might not see those. And so that's why oftentimes you see this broad peak for OHs. So for signals for exchangeable protons, such as those below, they will disappear completely. So if you have a sample with an alcohol, carboxylic acid, or an NH, those peaks will just go away. You add some acid in there or a solvent that will exchange the proton. So this is where the OH peak is here. And for some reason it's split, which doesn't always happen. But if you put it in deuterated methanol, so CH or CD3OD, it will become CHR1, R2, and then OD. So that signal will go away, which is why we don't see it here. So if you have an alcohol, carboxylic acid, or an amine in there, and you use the wrong solvent, that peak could disappear. Some patterns that you might see in aromatic rings, if you have a benzene that has one group, so this is mono-substituted, it will kind of look like a mess. This is a multiplet that integrates to 5H. Here you have benzene with two groups, so this is di-substituted, that is 1, 2. And then you'll get two triplets, and they'll probably integrate to 2H each. And then you have the 1, 3. And then you have this singlet, and then another mess here. It's kind of hard to see those ones. And then when you have the para-substituted or 1, 4 disub, there's HA, HB, and then you have 2H and 2H. So these give you two nice doublets here. So when you see these patterns, a lot of times it will tell you about the substitution pattern. If we are going to predict the multiplicity of this one, we're going to look at the different protons here and see how many signals. So number of signals first. This is HA. This is HB. So this carbon sees the same thing as this one. So this is also HA, HC, D. There's no hydrogen on this carbon, so we have HE, and these are all E's. All right, so we have 1, 2, 3, 4, 5 signals. So HA sees HB, so that will be 1 plus 1. And this will be a doublet. HB sees HA. There's 6 of them, so 6 plus 1. This is a septet. HC sees HD. There's 2 there, so it'd be 2 plus 1. This should be a triplet. HD sees HC, and there's nothing on this side, and there's 2 HC, so that's 2 plus 1. That should be a triplet. And then HE does not see anything, so that's 0 plus 1. That should be a singlet. So that's the multiplicity of each of those. If you had to take an IR of each of these, they would be difficult to distinguish by IR or MS, and that's because they would all have the same functional groups and formula. But we can use NMR to do that with protons. So this one would give 3 signals. You can see the different colors there. This one gives 4 signals. That one gives 2 signals. So proton NMR is going to give us a lot more information here. How can we use NMR here to distinguish between these 2 molecules? The only difference is that this alkene is in a different location than this one here. This one is HA. HA would see HB. It sees 1, so this would be a doublet. But on this one, HA would see HB, and there's 2 there, and that would be a triplet. So that is a really quick way to figure out what is different there. To analyze a proton spectra, if you have a given formula, you can determine a molecule structure by using a 4-step process. So the first thing, if you're given the formula, you calculate the RDBs, and then consider the number of signals and integration to look for symmetry. Analyze each signal and then draw little puzzle pieces that match the shift, integration, and multiplicity, and then assemble all the structures together like a puzzle. So if we look at our problem, the formula is C9H10O. The first thing you want to do is calculate the RDBs, so 9 times 2 equals 18, plus 2 equals 20, minus 10 equals 10, divided by 2 equals 5 RDBs. If you have 4 or greater RDBs, that usually will tell you have benzene. So we have a benzene of sorts. So this is, the ring is 1, 2, 3, 4. So we're going to have a benzene plus 1 other site of unsaturation. It could be an alkene, it could be another ring maybe, or a carbon double bond oxygen. The next thing you want to do is make a table. So I start with the delta shift, 1 for integration, multiplicity, and then I make a column for the neighbor. I'm going to start with integration. So these are not reasonable values for the number of proton on here. So I'm going to divide all of them by 10. So this becomes 1H. This is 5H. This is 2H and 2H. The first shift here is around 2.9 ppm. This is going to be a sloppy table. I'm going to run out of room. The integration is 2H, and that is a triplet, which means I have a CH2 next to 3 minus 1 equals 2, a CH2. So this is next to a CH2, and then I have something at 3.0. It is 2H. It's another triplet, so it's a CH2 next to a CH2. This triplet minus 1 is the number of protons next door. If we look at our tables, this is the region where the aromatic benzene rings show up. So you can do, this is 7.2, 5H. This is a multiplet. And this specific pattern is a benzene that is mono-substituted. So there's one group coming off of here. And then at 10.2, we have 1H. It's a singlet. This one here usually is one where aldehydes show up. Our pieces, we have a benzene. This CH2 is probably this one. So we have a CH2, CH2, And then we have an aldehyde. Okay, so you can add up your protons here. I have 2, 4 plus 5 is 10. If I tally up my number of carbons, I have 6, 7, 8, 9. So for my formula, I have C9H10. Everything is accounted for, so I just have to put these pieces together. So I have benzene. I can't put the aldehyde here because that would be the end of the molecule. Do the CH2s, and then I put the aldehyde on the end, and that's the structure there. I'm going to let you guys try to do this one. So you can start with your table. You have integration with the multiplicity. And the neighbor. So take a minute and make an attempt. So first do the RDBs. So we have 1 RDB. And then fill out the table. If you don't have the spectrum, it gives you something like this. You have the delta shifts at 1 ppm. You have a doublet that's 6H. So integration is 6H, and the multiplicity is a doublet, which is 2 minus 1. So there's one neighbor. So I know I can't have 6 hydrogens on 1 carbon. So I probably have 2 CH3s that C1CH. So these are the ones that I'm looking at. And then I have a 1.1 that is 3H here. That's a triplet. So that's 3 minus 1. So I have 2 neighbors. I have a CH3 next to a CH2. And then at 2.5, there's a quartet with 2H. There's a quartet, so that's 4 minus 1 equals 3. So I have a CH2 next to a CH3. And then at 2.6, I have a 1H. So this is the CH that sees 2 CH3s. So I'm going to tally up. I have 6, 9, 10, 11, 12. All the hydrogens are accounted for. And then my carbons, I have 1, 2, 3, 4, 5. So I'm missing 1 carbon, 1 oxygen based on the formula. So the pieces that I have, I can look through them. I think that this CH right here is the same as this one. And this CH3 is the same as this one. So if I put my puzzle pieces together, I have CH3 bonded to another CH3, and then I have a CH2, CH3, and that's that one. So the piece that I'm missing is a C and an O, and I'm also missing a ring or a double bond. So that could be carbonyl. And if we think about where the proton shifts are, so these ones that are around 2.5 and 2.6, that's consistent with hydrogens that are on carbons next to carbonyls. So my structure, check off that piece, and then I have the CH2, CH3, there, and check off that piece. So that is the structure. If you are starting to worry about what is going on and you don't understand, that's okay. We'll do a bunch of these problems in class.